Hello everyone, and welcome to MacDermid Enthone's discussion on the Enviralloy Sprint, an alkaline zinc nickel process. My name is Robert Collin. I am the Americas Technical Manager and will be the moderator for this event today. The presenter is Mike McCoy. He is the Anti-Corrosion Business Development and Product Manager. Please submit any and all questions you have in the questions section of this webinar. We will answer as many questions upon conclusion of this presentation. If we don't get to your question specifically, we will do our best to get back to you via email. And again, thank you all for taking the time to learn about MacDermid Enthone's Enviralloy Sprint and Alkaline Zinc Nickel process. With that, Michael, the session is all yours.
Good morning, everyone. Mike McCoy, Product Line Manager and Business Development Manager for Anti-Corrosion Coatings. My field has been pretty much related to anti-corrosion coatings for the last 25 years. I'm very excited about this product. I have been able to see improvements in productivity and throughput, not only in our pilot facilities by running customer samples and trials, but also in field studies in the Americas and in Europe. I apologize for the delay. So what we're talking about with the Enviralloy Sprint is a change in philosophy compared to conventional alkaline zinc nickel systems. Rather than using sodium hydroxide as a conductivity salt, we are going to take advantage of the benefits of potassium hydroxide being a better conductivity of current, which leads to higher efficiency, more throughput, and increased productivity. And that's really what we're talking about with this process, increased productivity. So if you're an applicator, and just for round numbers, say it takes you one shift to do 10,000 pounds of fasteners, and if you're able to use the Enviralloy Sprint process, we've actually seen where in that same time frame, you're going to be doing approximately 12,000 to 13,000 pounds of fasteners in that same time frame. So we're talking about an increase of 20 to 30% in productivity in the same time frame, which, as we all know, that is extremely beneficial. It helps to decrease the need for large investments like adding on plating lines or adding on extra plating tanks. The increase in conductivity really matters a lot in lower voltages, so there's less strain and requirement for cooling capacity. The system operates very easily, very standardly to a standard sodium-based system. One of the advantages that is a disadvantage for sodium system is that you wind up with sludges and crystallization that forms on the anode and other equipment that at some point in time needs to be removed. That's going to create downtime. We do not have that same issue with Enviralloy Sprint. It's a smooth, nodular-free, semi-bright silver-colored coating. One thing that we know is that this is a particularly bright bath. We know that the increase in efficiency will change the grain structure. And I have some pictures coming up in a couple slides, but as a deposit is more smooth, less nodular, your eyes are going to see a brighter surface like a mirror. And your eyes are going to pick up a brighter deposit rather than a duller deposit that might be a little bit more matte or a little bit not as refined. And that goes to the fact that we are using a potassium system at a higher efficiency level. We are still going to maintain excellent corrosion resistance. That does include higher corrosion resistance after heat treatment. And we're going to have standard alkaline thickness distribution and alloy distribution that we have obtained from other systems. We're going to maintain that sweet spot of about 12 to 15% nickel, which is what is required by most OEMs. So back in the sodium systems, we're looking at an efficiency of about 35 to 45%. When baths are used and made up brand new, they're going to be higher, and the efficiency is going to be reduced over time, pretty much because of sodium carbonate, but also to a little bit of a lesser extent, some of the breakdown products that are associated with the organic additives in zinc nickel systems. A few years ago, we have improved our sodium systems to raise up the efficiency to approximately 55 to 65%. But more than that, we were able to reduce some of those breakdown products. And breakdown products, as anybody who has run zinc nickel, are extremely important. You basically don't want to destroy the heartbeat of the system, being the systems that have these products in an inverse relationship to good versus bad. For instance, if you have a complexing agent that all alkaline systems have, that's the good products. The breakdown products from those complexing systems really inhibit the efficiency, slows down the system, increases specific gravity, and need to be removed. Also with the sodium carbonate, it has to be frozen out. We've all has used zinc nickel, have had to deal with freezing out sodium carbonate, whether on a routine basis or whether on a batch basis. With potassium, we have improved productivity, and improving the productivity, we are using a potassium hydroxide, and potassium carbonate cannot be frozen out. So in order to maintain your high efficiency, we are either going to rely on two methods. One, bleed and feed, or two, drag out. This system was originally developed for barrel processing. Although we do have rack operations, in barrel processing, we anticipate high productivity and therefore more barrels per hour. More barrels per hour means more drag out. More drag out means hopefully a stabilization in potassium carbonate concentration, and would remove the need for any sort of bleed and feed type of operation. So talking about numbers and efficiency, and you can see that over time, standard alkaline technology will be reduced over a bath aging of approximately 100 amp hours per liter. The improved 1215 G2 is similar, although a little bit better, because it doesn't break down as much of the organic components. The Sprint process, you can see, does have a reduction in efficiency, but we're starting out at a higher level of efficiency. And when it does reduce, it levels off at a higher level of efficiency. So the benefits between 60% and 80 to 90% are significant. Again, these comparisons are made against each other and are being operated under identical conditions. So when we talk about the need for bleed and feed, what are we talking about? We're talking about the specific gravity of the solution. We're talking about breakdown products that take up space in that solution. There's only so much stuff, so to speak, that you can put into a gallon of solution, whether it's water or zinc nickel solution. At some point, there's just too much stuff that can't handle and can't be solubilized, and things start to split out. So we monitor the specific gravity. As mentioned, carbonate will not freeze out on Sprint because of the potassium hydroxide. But we can monitor the solution in an overall sense, not just the analysis for potassium carbonate, but an overall sense of how much loading we have into that solution. And we can follow that by specific gravity. And you can see on the lower portion of this slide, we talk about a rate of approximately, in a rack operation, 25 liters per 10,000 amp hours. And in a barrel operation, significantly less than that. We'd like to get down to, and if productivity is high enough, where we don't need to have any reaction to a higher specific gravity. But if we do, we could be looking at as much as only 6 liters per 10,000 amp hours. Again, Enviralloy Sprint is designed to improve conductivity. And that's what we're talking about here. Improved conductivity equals improved efficiency equals improved conductivity. Faster deposition rates. And I have some customer examples that I'm going to explain later on in this talk. The reduction in voltage and heat treatment, I found out that firsthand when I first started looking at this process in our pilot facility. 2 reasons that I saw. One, I was using a smaller type of tank, but I was only drawing 1 volt. I had a 6x6 inch barrel in a pilot lab facility drawing 1 volt, and I had plenty of amperage, but I noticed that the barrel was not gassing. In a standard sodium-based alkaline zinc nickel solution that is brand new, everybody knows it's bright purple. And when you turn on that current, the bath almost explodes with hydrogen. We are producing so much hydrogen because of the lower efficiency that you can see tremendous amount of gassing in the tank. When I was doing my trials, turned on the current, only saw 1 volt and saw no gassing coming out of the barrel. So what does that mean? We're depositing metal rather than evolving hydrogen. That's what that efficiency goes to. How much metal are you depositing versus how much hydrogen are you producing? Same can be said for acid electrolytes and alkaline electrolytes, right? Acid electrolytes have a higher efficiency, less hydrogen, faster plating rate, better metal deposition. We see similar type of comparisons between Enviralloy Sprint potassium-based and any sodium-based system. One of the other advantages, as I mentioned, is that we don't have any sludge or scale on the anodes. That reduces that need to be removed and creates downtime. A picture of what some of those oxalate crust and scales look like. These do need to be taken care of at a certain time. I was recently at an applicator that had not performed any maintenance in a few years, and they had sludge on the bottom of the tank almost up to the barrels. You don't have the same issue with this system. No carbonate precipitation, high efficiency, no carbonate on anodes. Sodium carbonate will come out of the solution very readily. It's one of the first things to get kicked out, and that's part of the sludge that's on the bottom, even though it's at a warmer temperature. But more importantly is this oxalate on the anodes themselves, or any sort of material on the anodes. We all know that the anodes need to be clean and that they need to be efficient. And in sodium systems, this issue needs to be addressed with, or your solutions will not operate properly. Again, higher productivity, less downtime. A nice benefit about the Enviralloy Sprint is that it can be run rack and barrel out of the same plating solution. Most conventional alkaline zinc nickel systems require different metal concentrations and, more importantly, different brightener packages. Rack operations contain more anti-burn, high current density type of components, while barrel, because you're plating at a lower current density, obviously have lower current density additives in place of anti-burn components. In Sprint, you can run the same bath and do rack and barrel processing at the same time. To my point earlier about the efficiency, the higher efficiency produces a less granular, less nodular film. You can see on the right with the conventional process, you have some nodulation there, even after passivation. The Sprint, because of the efficiency, the grains lie down in a much more uniform manner, are less granular, even after passivation, and therefore also is what is providing your extra brightness. So what does that mean for an applicator or an OEM? The less additives that we need or are required to put into any plating solution to add grain refinement have a possibility of being overdosed. If you can decrease the amount of grain refinement additives that are needed in a solution to produce a brighter deposit, the possibilities of having blisters or pore adhesion or delamination, or particularly in any zinc nickel system, you saw some tubular goods on the previous slide. A lot of people like to plate and then post form parts, bending, crimping. The Sprint, and we have seen this in a few operations, is much more ductile than conventional systems because the organic additives required for a bright finish are reduced compared to conventional sodium systems. So how do we operate this bath? Fairly standard operating conditions, except for the fact that you can run the Sprint a little bit warmer than you can a conventional system. Conventional systems at higher temperatures, that organic package, the complexing agents and whatnot, will break down significantly. Not with the Sprint process. One of the main characteristics that is very similar is the need for a high anode current density. That is still true with Enviralloy Sprint. 50 ASF and higher is recommended and needed for all alkaline zinc nickel systems, and that is the same for Enviralloy Sprint. So when we start talking about additives, you'll notice that I've been mentioning the word Enviralloy Sprint, and that's because we have learned something since this product was released a few years ago. And one of the things that we learned is that by starting to add in a product called Enviralloy 1215 Part B, which is an additive that we use for our #1 selling alkaline sodium technology system, we reduce the amount of needed add backs of the carrier. And the carrier is your complexing agent. The term carrier in this instance is not like an acid zinc carrier where it's a wetting agent. This carrier is the actual complexing agent that holds nickel in solution at a pH of 13. Under normal operating conditions, by introducing some of the 1215 Part B, we start to be able to reduce the amount of carrier that is needed, which significantly reduces the cost per pound, per amp hour, however you want to categorize it, reduces the cost of operation because the carrier consumption is reduced. The nickel additive is going to be one of your more high level of consumption, and that's because that's what's getting deposited on the plating bath. And it's not because we're plating out 30% more nickel. It's because we are productively putting through more solution or more product when you start talking about an amp hour basis. So as I just mentioned, the carrier stabilizing agent, Sprint ZnNi, that's your nickel replenishment. It doesn't come off of an anode. It has to come in over the side as a liquid additive because it needs to be in solution before it hits the plating tank or it'll precipitate. Brightener is a fairly standard brightener additive. LCD is low current density additives that are needed over time. And as mentioned, the 1215 Part B is just an additional stabilizer, and it helps to reduce the consumption of the carrier. So what are we talking about for dosing rates per 10,000 amp hours? And this is, if you look at the first item being the Sprint carrier at 1.5 liters and the Enviralloy 1215 Part B at 1.5 liters. That's 3 liters per 10,000 amp hours. In the previous system, before our upgrade in technology, we were looking at rates of more like 4 to 5 liters of carrier per 10,000 amp hours. So we have significantly reduced the cost of operation for the applicator. Again, this is all relative according to drag out, rack versus barrel, and throughput. As this is mentioned here, it might look like a lot of additives, but we really can mix the NI, the carrier, and the Part B. That could be on one feeder, a second feeder for the brightener, and then the LCD would only be added as needed per hull cell analysis. So this also goes to efficiency. This also talks about specific gravity. And since it is the #1 cost driver, when we talk about 8 to 15 liters per 10,000 amp hours, we're talking about 20 to 50% more nickel consumption compared to sodium process. That's because it's more efficient. We don't need to have sticker shock by looking at that, but it's something that needs to be noticed. We are running more parts. More nickel metal is being deposited per hour. Therefore, that consumption looks abnormally high. But again, it's analyzable. And if you level off on a drag out rate, then we can certainly run on the lower side of that range. An important thing to mention is that the line setup for this system is very important, as it is with any zinc nickel. Using corrugated anodes, as in the picture, will significantly reduce and significantly break down the complexing agents. And by significantly, I mean very fast. And then you have organic contamination to deal with. So without overstating the anode current density, it is probably the #1 issue that you have to deal with when putting in a new line. Some of these complexing agents and some of these products are very expensive. The last thing you want to do is purchase them, use them, break it down before it is ever functional, and then have to deal with the breakdown products. So it's always recommended to have differences of advice on anode configuration. At MacDermid Enthone, we have this concept very, very close to our heart and very, very close to our customer base and our technical service team. And we know how to design the anodes for the optimum consumption and optimum utilization of those complexing agents. We need them, but let's make sure we use them efficiently. And again, over 50 ASF is required. So a very small anode area. I didn't mention it, but it was on the last slide. We can also use plain mild steel anodes. We prefer them to pure nickel anodes or nickel plated anodes. And that goes to the benefit, again, of breaking down the complexing agents in the electrolyte. So in cases where we need to do bleed and feed, we are really just trying to maintain efficiency, trying to decrease the viscosity or the specific gravity. And again, that goes to increased conductivity. We're starting out on a high level. Let's not go ahead and do anything that's going to lower it any more than we would expect. So therefore, again, you can see on the graph with the bleed and feed at greater than 1.26 specific gravity, we're going to maintain that high level of efficiency. And if we don't, we're going to see a decrease down to below 50%. So again, 20 to 25% increase in production. That's what we're talking about here. That is what really gets this system to the top of the list of preferred systems for alkaline zinc nickel. The other thing before I talk about customer experiences, in generalities, what are we talking about? Fasteners, right? We're talking about plating fasteners in high production environments. When we start getting into higher strength steels, we all know that the OEM industry, the automotive industry, is reducing weight on vehicles. Therefore, they're going to smaller, stronger, high strength steels as fasteners. Save weight. We have applicators, and we know of instances where the initiation of a system that has an efficiency of 45% is not going to initiate on a 12.9 bolt. It's not going to initiate on a high hardened steel like a 12.9, or even some of these exotic alloy steels like molybdenum, or other metals and other alloys that are put into the steel to increase that strength. The higher efficiency allows us to create faster initiation. So right off the bat, if you're an applicator that plates high hardened steel all day long, you're not going to be plating for 2 hours because the initiation never takes off. The Sprint, we have seen and know that it can plate high hardened fasteners very, very readily on a very consistent basis. And that's another extremely advantageous point to this system. So a couple customer experiences, and I think this will go in line with my previous slides. Out of these, only one is barrel, but if you notice, they don't do any drag out. The rack customers, rack plating doesn't drag out that much, so we're looking at 25 liters per 10,000 amp hours, which is about what we were expecting. And the NI, the nickel additives, we've seen that are pretty much in line as well. You can see the bottom customer is below 10 liters per 10,000 amp hours, but all the other experiences, whether it's an 8,000 liter or a 34,000 liter bath, are all fairly consistent. And the ratios between the carrier and 1215B are approximately what we would expect as well. The overall add backs are not a lot for this system. So in a rack operation, we have an applicator that does use bleed and feed 25 liters per 10,000 amp hours and was able to reduce his plating time from 80 minutes to 60 minutes while still obtaining the same thickness. It's a big number, 20 minutes. It's 20 minutes saved every single rack, every single shift. In a barrel operation, we've seen plating times reduced from 60 minutes to 45 minutes and no requirement for bleed and feed. So we're getting more barrels per hour. We're dragging out more of that carbonate. We're dragging out more of the breakdown products from the complexing agents and the brighteners and whatnot. And we're able to maintain a very bright finish as well. So again, lower carrier consumption reduces cost. That was one of our number one cost drivers when this product was first released, and we've addressed that. Plating bath doesn't really burn. We've run high amperages and we have seen no burning. And it's been very, very good performance in that rack application. And also the LCD is good as well. There's not a lot of troubleshooting to clean up dull, low current density areas. And we say Enviralloy Sprint will replace Enviralloy Sprint. That was the move to adding the 1215B. That thought process was originally discovered in some of our European clients, and in talking to some of my colleagues in Europe, as soon as the technical service team found out about that this additive would lower carrier consumptions, we just put it in across board and never had an issue. We just made it, we lowered the carrier rate, we started increasing the 1215B rate, and everything got reduced. And the less stuff that you have to add to the plating bath, the more efficient it will be. So some of the other customer findings: higher plating rates, good production parts, even at higher levels of potassium carbonate. The potassium hydroxide runs at a similar concentration to sodium systems, about 120 to 130 grams per liter. Again, they've also found the same things that we've been talking about: high conductivity, less energy consumption, less strain to put on the cooling system, nodular-free, bright deposits, similar metal distribution, uniform appearance, no sludge, no scales on the anodes, no freezing out when you are running a high productivity shop. So one thing that we've actually done is we know, based on pure math, what level of productivity is needed that I can take advantage of this system, not have to freeze parts out. I'm sorry, not have to freeze carbonate out. Parts are going out the door at a higher rate. So this is a system made for a high productivity shop. This is not a system that's made for someone that just has a zinc nickel tank in the corner and runs zinc nickel every once in a while per customer demand. We've worked out the numbers. We know the level of throughputs where this is advantageous versus where this is so disadvantageous we wouldn't recommend it, and we would recommend a sodium system. And we have that data, and it's valid. So with that, I will answer any questions that you happen to have. If Rob has captured them, I'd be happy to answer them.
Hi, Mike. So we do have one question for you so far. What is the average thickness in the rack application at 60 minutes? And the same as barrel, what's the typical thickness in 40 minutes?
I saw that information, and for a rack process, 60 minutes does seem fairly long. Every line is different. You know, we deal with that question a lot, actually, in our pilot lab. We run different plating jobs for different potential customers or existing customers that just need some work. And that actually is one of the bigger questions that our team has to look at is, how is the plating solution functioning today? And how long do we have to plate these parts to obtain the required thickness? Most thicknesses for zinc nickel are minimum 5 microns, standard 8 to 10 microns, and too high would be 13 to 15 microns. Because of the increase in nickel, into the zinc nickel deposit, ductility does become an issue. It's not as much of an issue in this case, but because the Sprint is more ductile, but you never want zinc nickel to be over 13 microns because you have the susceptibility for cracking and delamination. You need 5 to 8 microns to meet your standard 1,000 hours of salt spray. And those examples from our customers where the plating times, especially on the racks, seem to be a little bit longer, might just happen to have some sort of unique capacity. But we always shoot for pretty much 8 to 10. And based on the line design, every line is different. Every line operates differently. You should really be able to obtain that in your 10 microns in about 45 minutes maximum. And a barrel application, that 45 to 60 minutes was pretty much spot on in my mind. For a potassium-based system, that 45 to 60 minutes can produce 8 to 10 microns. Again, depending on what part you're dealing with. I have a customer that plates zinc nickel for 2 hours because the parts that they're doing have a Rockwell hardness of 55C. So it takes them forever to plate in a sodium system. In the potassium-based system, we got them down to 75 minutes, 75 to 90 minutes. So reducing from 120 to 75 to 90 on this particular part at this particular customer was very advantageous for them.
Great. Are there any controllers that can add the additives back based on, say, density or any other means?
At this time, no. Although it is based on specific gravity, we have not come to the automatic bleed and feed type of scenarios that I know is popular with some electrolyte nickel, which kind of works on the same premise of specific gravity. But for this system, we have not reached that level of technology yet.
Okay. Is this product suitable for, rack applications of, small batches of larger size parts, say greater than 10, 12 inches, with a thickness of, say, 15 to 18 microns?
It could be, yes. Again, at that thickness, I would be concerned about post-plating bending and crimping. But yes, it would be fine for larger type parts. Just like any alkaline system, the larger, you're not going to want to do it in an acid system, but the alkaline system would be very beneficial for that. And in this case, I think it would be beneficial for throughput as well.
Great. How is the passivation on this zinc nickel as far as blacks and things of that nature?
Very standard, excuse me, standard to conventional systems. There is not a need for an additional type of passivation or sealing operation. The black passivate looks very, very good, very uniform. The black passivate is based on the nickel in the deposit. And because we're uniform high to low, we get a very, very good looking black passivate. The clear passivate looks very bright. It's matte, but it's shiny, if that makes any sense. So it is as any zinc nickel, it's a functional coating, right? It's not going to look like nickel chrome. It's not meant to look like nickel chrome, but passivation is performed very readily and very easily. One thing that does need to be noted, though, when talking about passivation, and that's simply potassium hydroxide versus sodium hydroxide. Potassium hydroxide does not rinse as well as sodium hydroxide. It's just a fact. Therefore, when talking about passivation, the rinsing operation between the plating tank and the passivation really needs to be good. You probably would not be able to get away with one in and out of a rinse and then into a passivation. You're going to be dragging in so much potassium hydroxide that your pH is going to rise. You're going to get streaks. So rinsing prior to passivation is extremely important and more important in a potassium system than it is a sodium system.
Great. And then the final question we're going to have for this system and this session is, are there any part type as far as base metals that are that can't be used? Like, can they process through the systems without issue?
As far as base material?
Yep.
Well, cast iron would not be recommended, although you'd have a much better chance doing it in this system than you would in a sodium system because of the efficiency. Compared to other alkaline systems, it's pretty much going to follow the same guidelines. You could do forgings if you wanted to. You could do high hardness, like I said, molybdenum-based steels and other exotic alloys that these guys are coming up with to increase strength while decreasing weight. You know, the metal finishing portion of developing a fastener is the last thing anybody thinks of. So they're going to put in any exotic metal. It makes it more difficult for us. We've all seen that 100 times. So the sprint process compared to sodium-based systems will be more advantageous to plate those type of exotic alloys.
Excellent. Well, thank you very much, Michael. It was a very informative session. And to everyone that participated to listen, thank you very much again for listening to Mike talk about our Enviralloy Sprint Alkaline Zinc Nickel process. Again, if you'd like more information on this process, please email Mike McCoy directly. For those questions we did not get to, we will follow up with you via email. And the session will be available for watching again on our website. Thank you all again for attending. Stay safe and enjoy your day.
Thank you, everyone.